All right. Good afternoon, everybody, and welcome to today's edition of the Halmstad Colloquium. It's my pleasure to introduce to you today Kersten, who has completed her master's studies in Rostock University and is currently a PhD student working on enclosure methods and including optimization methods for uncertain and nonlinear systems. It's particularly cool to have her here since part of her talk is already an award-winning talk. It had received Best Young Researcher Award at the Methods and Models for Automatic and Robotic Systems. So without further ado, welcome, Julia.
Well, thank you for the introduction, and I'd like to welcome you too. As Walid already said, that we're working on uncertain systems. Uncertainty in this context means that we have bounded uncertainty. That means we're working with intervals. We have a lower and an upper bound for our worst case scenarios. So that being said, 2 years ago I had the idea that if we have an uncertain state and we control the system with the uncertain state, then we have to adjust the controller gains up until a certain point, and then we could use a constant gain feedback. The main idea behind this was that if the system is controlled and it goes into its equilibrium, then the interval width of our states should reduce as well. So that was the idea, and I implemented this, and those were the controller gain results. And as you can see, they adapted for a short period of time, and then they got constant. So actually seems like quite a good idea. Yeah, the bummer was when we simulated the system, the state, the uncertain state, did something like this. So as you can see here, we have an initial uncertainty interval, and it reduces, and then it blows up. So as we already seen that the controller gains themselves do as we please, the problem here can't be in the control itself, so it has to be somewhere else. And well, what is the other thing that can cause this problem here? Well, it's the simulation. So that means that in the simulation, we, by using the prediction for our simulated states, there comes into play the so-called Webbing effect. And that means that this overestimation of the initial state here is just because of the Webbing effect. So, as you can imagine, I was a little bit bummed about this solution here, and to try to cheer me up, Andreas gave me a paper from some colleagues from Tarek, Gracie, and Dennis Efimov, and they introduced me to Cooperativity. So, Cooperativity is a mathematical structure where you can decouple your systems and simulate the worst case bounds as decoupled systems, which is shown here for example where we have uncertain states. So an uncertain state in our system matrix would mean that we can, for cooperative systems, simulate the lower bound and the upper bound decoupled and or separately, and then we get the solution inside those bounds. And well, this may seem to like a trivial solution to you, but the problem with intervals, or when dealing with interval arithmetic, is that we cannot always use this. This can just be done for cooperative systems. So when we use cooperative systems, we could simplify. Well, this is the main point which what I was trying to do. We could simplify the computation of the guaranteed state enclosures, as well as simplify all other or main many other applications for control engineering, because for the we wouldn't deal with intervals anymore. We would deal with two separate known systems. So this is basically the overall idea of cooperativity. And yeah, what is cooperativity? When we consider an autonomous system, and please be reminded the autonomous system here is kind of important. The Jacobian matrix, which would result in our system matrix, needs to have all off-diagonal elements to be non-negative. So this is also called the Metzler structure of a matrix. That means for the positivity of the system, we guarantee that all state trajectories starting in the positive orbit stay in this positive orbit. So that means that this would avoid that crossing those decoupled systems, and thus failing to use or failing the mathematical structure of cooperativity. So this is just a slide so you can understand our nomination. Those are the interval representations with an upper bound and a lower bound of the interval. Okay, so the good thing is there are some cooperative models which can be derived by the first principle. This holds true, for example, for thermodynamical systems, for fluid mechanics systems, for biochemical systems, as well as for Markov chains, for example. And the resulting ODEs for these systems of nodes would be like this. So, and if we now have a look at the StateSpace representation, we can clearly see that all off-diagonal elements here are clearly non-negative. This here, the negativity on the diagonal elements further represents Hilbert stability, which is also required if we want to continue or if we want to use our autonomous system in a stable point. So, unfortunately, the system I presented to you earlier, well, what can I say? It's a mechanical system, and mechanical systems do not fall under this cooperative systems while derived from the first principle. So what are we doing if something does not have the form that we want to acquire? Well, we can screw around a bit mathematically, and screwing around in this case just means that we find a transformation matrix that requires our system to be cooperative. So we consider the quasi-linear, or we consider this system to be given in a quasi-linear state-space representation for nonlinear systems. Well, if the system is linear, this will hold. And for nonlinear formulations, we can factor out our selected state variables, and this is now an advantage in using uncertainty, because those state variables can be considered as the uncertainty. So, in order to get cooperativity, we need our system matrix to be Metzler and Hilbert. Hilbert because of stability, while Metzler because of the cooperativity. Okay, so I already told you that not all systems are cooperative. This is the these are some preliminaries to take into account in order to transform the system. I showed you that we're taking into account an autonomous system. Autonomous system in this case can also mean that we include a feedback controller according to those equations, and that means that our Metzler structure is given in our controlled matrix. So after all, we consider this to be an autonomous system and just assume, because of preliminaries, that our system matrix is already controlled. So let's have a look at general transformations. Well, generally we consider diagonally dominant systems. And thus we need to transform most of the systems into a diagonal dominant form at first. And this is done as such. Well, I think most of you may know how this is done. So, yeah. Furthermore, we will have to transform in the next step this diagonal dominant system matrix into a Metzler structure. So after all, it's a two-step transformation. Okay. On the paper of Tarek and Dennis, they proposed a method where we take into account the eigenvalues of the system. The problem here is that we need to distinguish between purely real and complex conjugate eigenvalues. So for purely real eigenvalues, our transformation matrix can be or is time invariant. Unfortunately, for our complex conjugate system, the transformation matrix becomes time varying. But I'll get to that later. So let's start with system with purely real eigenvalues. And here I need you to bear with me because most of those equations stem from the paper of Tarek and Tarek and Dennis. So I'd like you to shift the responsibility of those equations to my colleagues there, because I only took their equations and made them, or I used them to be more general applicable. Because, I'll explain their method and then I'll tell you why it's so difficult to do them by hand. Well, as you can see, at first we have a diagonal dominant matrix ZA. And our uncertain, which is a midpoint, or which can be considered as a midpoint matrix, and the uncertainty is shifted into this delta. So that means that we have the delta consists the worst case bound of all the whole uncertainty matrix. This means that we widen our uncertainty a little bit with this delta, because well, we have to take into account our the worst case. And we're searching for a Metzler matrix R, given in this structure that has the same eigenvalues as our ZA. So this means if there is a matrix R which has the same eigenvalues as our ZA, then we have an orthogonal matrix S which can transform the system into a Metzler form. Well, provided that this holds, but let's get to that later. So, as you may see, this sounds quite complicated. And for, let's say, smaller problems and systems with lower orders, this can be done by hand. And Tarek and Dennis provided some examples, which they just did by hand, I assume. The problem is, if you implement this for real-life applications, it becomes quite difficult to perform per hand, because, if we take into account, for example, the system I showed you before was an order 4 system. So to manually compute those matrices would be very difficult. So what we're trying to do is to find a computational feasible optimization to find this transformation matrices. And we're doing this by applying LMIs. So let's do this step. At first we need to choose the diagonal matrix ZA. ZA is already chosen if the system itself is diagonally dominant. Then ZA, the choosing of ZA is quite easy. If the system is not diagonally dominant, we transform this at first, and then we choose ZA to be the diagonal matrix with the asymptotically stable real eigenvalues of the midpoint of the controlled matrix. The choosing of the delta is related to this ZA because, as you may remember, we need the worst case bounds. So we need to maximize the difference between our originated matrix and our chosen ZA. And well, further specification is just the, let's just say, Tarek's equation to take into account, and to mark the lower bound. And well, this is an equation he required, and we implemented this one as well because of the orthogonality of S. So to write this as an LMI, we convert our matrix inequalities with a Schur complement into this form. And well, the known specifications are just implemented as LMI constraints or in the overall cost function. So keep in mind, this is our orthogonality. This is well our gamma stability, which is related to our mu. And well, you have to keep in mind that this part needs to be linear, a linear matrix inequality. So in order to avoid the LMA constraints or to avoid complicating those solutions, we take the last successful evaluation of our S into account and then put it in our constraint to keep it linear. Okay, so this was, let's say, a more complex form of a transformation, but this is just because taken into account all these equations from Tarek and Dennis. So now we presumably get to a more simplified version because of the conjugate complex eigenvalues. But don't be fooled because I get to the problems of this implementation later. So with purely conjugate complex eigenvalues, the uncertainty itself is shifted into the positions of the eigenvalues. That means that we have the eigenvalues themselves have a lower and upper bound of the real parts, as well as a lower and upper bound of the imaginary parts. So let's assume, this is quite important too, because if we have those eigenvalues need to be disjoint. Well, why? It's quite easy, because if those would overlap, we will know the worst case bounds of the eigenvalues of the separate eigenvalues. So this just holds for disjoint eigenvalues. The number of the eigenvalues to be considered is reduced as well because of the conjugate complex pairs. So these are just some minor preliminaries. And yes, now let's come to the transformation itself. We know that we can transform the system into a Jordan canonical form by a transformation as such. So if we use the Jordan canonical form and derive our state space representation, we will get this part, and this part will be the new system matrix. And we know that our new system matrix, with those constraints of before, will result in a Metzler structure that just consists of the real parts of the eigenvalues on the diagonal. So we know that just by calculating our worst case bounds for the eigenvalues, just the real parts, we know that this is our resulting Metzler structure, definitely Metzler structure system matrix. Well, this is great because, well, it's very easy to calculate this matrix. However, it's not so easy to calculate those exact transformation matrices. But I get to that later. So, yeah. Okay, I already told you that. Okay, let's have a look at our application scenarios. And now you may mock me a little bit on this, but let's get to that. This is our system with purely real eigenvalues. Let's just assume that I force the controller to produce this system with just real eigenvalues. So this is an inverse pendulum, and we are controlling the upright position. And well, as many of you may know, those are the nonlinear differential equation, which can be reformulated into a quasi-linear state-space representation. So quasi-linear state-space representation here means that we have the state alpha in our system matrix. Well, in our system matrix as well as in our input matrix. Well, since the system is controlled, we will get our controlled system in that structure. Well, this structure is clearly not Metzler. So now we are trying to transform the system. And yes, I know you are allowed to mock me on those highly uncertain states, but we'll get there later as well. So bear in mind that our system needs to have real eigenvalues, and those are given for this uncertain interval. The eigenvalues are real. So we apply our LMIs, and we get a transformation matrix consisting of the S, which is the result of our LMIs in the Metzler structure, and our V, which is the diagonal dominant part. So the transformed system results in this structure. I know a lot of numbers, so just have a look at the diagonal entries, which are all negative. That means the system is Hilbert's, and all off-diagonal elements are positive. So let's have a look at the system with purely conjugate complex eigenvalues. Here we have the oscillation of a wind turbine. And well, the equations are, it doesn't really matter what exactly is in this system. It's just what we can derive those differential equations, those state space representation with uncertainties in 3 parameters. So, and well, this is now quite easy because those uncertainties are not states, which means that this results in just a parameter-dependent system matrix. So that means that we only need to build the hull over our eigenvalues to get the worst case bounds for the real parts and the imaginary parts. So, and as you can imagine, or as I already said, for our Metzler matrix, or for our matrix to be Metzler, and to have this cooperative structure, we only need to take into account the real parts. So, as you can see here as well, this is clearly a Metzler structure. And now we have a look at our transformation from the states. Because keep in mind that it's quite easy to transform those system metrics for the purely complex conjugate eigenvalues. But the building of this transformation matrix itself is not so easy. Well, it's not so. There are some drawbacks to be taken care of. For this system, it was quite easy because we just took into account the worst case bounds of the eigenvectors, real parts, imaginary parts, for both pairs. And well, we transformed here the initial state as an example. Okay, so let's come to the conclusion. I showed you that those systems which are not cooperative from initially derived principles, they can be transformed into cooperative systems. And cooperative systems have some advantages. For example, avoiding the wrapping effect and therefore simulating, or while simulating lower and upper bounds separately. And that means that they reflect also, because of the decoupling, they reflect also the behaviors of known systems. So for purely real eigenvalues, I introduced you to an LMI approach, and the complex values, well, they were quite easy to introduce. So let's come to the drawbacks. I wrote it here as an outlook, which is quite a positive formulation, because I'm right now working a little bit more on the implementation of such. As I told you, I took into account the inverted pendulum as an example for purely real eigenvalues. But to a great surprise, when you have a look at the root logos, those eigenvalues are pure for the whole interval. That means, well, of course, I wanted to take into account a wider interval. And when I put a wider interval in the simulation, well, it didn't work. It didn't work because my approach is for purely real eigenvalues. So what did I do? Well, I used the complex conjugate parts, which are also valid for real eigenvalues. The problem is with those real eigenvalues, if you put them into the approach I showed you today, there is some slight overestimation for real parts. But this is not the biggest problem here. The problem is if you have those wide complex conjugate, or if you want to take into account those complex conjugate pairs. You have this transformation matrix. So in this transformation matrix, here we use the hull over all eigenvalues and the hull over all eigenvectors, of course, here, and the eigenvalues. Well, the eigenvalues are not that difficult because the meta structure won't be destroyed, but building the hull over the eigenvectors for such a large interval, for such a large uncertainty, this could result in some transformation matrices which are so big in their uncertainty itself that there may be a singularity in transforming them. Which means that if you cannot invert your transformation matrix, well, it becomes useless for your system because well, you need to retransform those. Well, just take a step back. This is the initial state. We would transform the system into the cooperative coordinates, but after all, after simulating, we would retransfer them into the original coordinates. And this retransformation could not be done if the transformation matrix isn't invertible. So yeah, that's a big problem here, and we try to solve this by introducing, for example, well, what you have to do here is you have to reduce the uncertainty in the transformation matrix. And we tried this with introducing complex valued transformations, which could work for some problems, but well, the inverted pendulum it didn't solve the problem with the inverted pendulum. So what we tried with it is the exponential technique that Andreas introduced to you yesterday. And now we're working on a joint solution in kind of combining the cooperative systems with this exponential enclosure structure. And, yes, this is the currently working mode. And after that, well, maybe we can even extend the system to multiple eigenvalues and in a joint approach for those presented procedures. Yes, that was all from my side. You can read a little bit on the details in those papers, and thank you for your attention.
Thank you very much, Julia. Questions from the audience?
Yeah, an actual question about rotation matrices. I work quite a lot on them and a lot of publications on rotation matrices, but I've never sort of used this LMI approach that you use. I usually use some optimization on the manifold itself, or doing something else, some kind of spectral factorization or something like that, or direct parametrization. Here you have this kind of small blocks, like in the Jordan form, you get this it's small 2x2 rotation matrices on the diagonal. It seems like, right?
Oh, okay. Yeah. I think we have to decouple this a bit.
Yeah.
Because the Jordan Jordan canonical form presented here is not done with LMIs.
No, exactly.
Yeah. So the real eigenvalues. It was kind of an optimization with LMIs. So we try to find a way to introduce all of the equations and all the formulations and definitions of Tarek and Dennis to reformulate them as such as an optimization problem. And this was kind of difficult to do in another way. So we ended up using the LMIs.
It's a nice approach. It's just that I usually try to solve it on this, for example, SO3 or what it is, the type of the manifold, and instead of just putting it as an LMI and together with some other constraints it's a nice.
No, I think the drawback of the LMI is that you have to put a lot of thought in this beforehand.
Yeah.
To reformulate those, and especially for example, for the cost function, we tried a lot of different things when before we ended up with something that really worked. So I think the problem in LMIs is that you sometimes forget some things. You may have to tell the optimizer, but because otherwise it was stuck on trivial solutions like zero.
But was this were you relaxing some of the constraints in your formulation? I mean, the last term was this trace identity minus SS transpose, for example. That is really a natural term, I think, in the not here, but exactly there. But is this so? This is you have not relaxed anything with this formulation.
No.
Right? No. Okay. So exactly. So okay. Yeah. Oh. No, it's nice. This part I liked, and then I also liked the Metzler part, the positive system part. It seems like these two concepts are in some sense very, very hot, and it's interesting that they both are appearing here. Okay, maybe LMIs, it's maybe 10 years back, but the combination is kind of interesting, I think, to solve this problem. I think it's a very nice presentation.
I'm interested in finding a system where the eigenvalues are definitely real. Because, as I told you, I tried this with the inverted pendulum, and I was wondering why it didn't work. Well, of course it didn't, because we have the conjugate complex pairs, and also I'm wondering if. But because the simulation time of this was quite high, maybe you wondered why I only did this for this small interval. Well, because it just it cost, I don't know, two days or something like this. So I was wondering if there is actually a system where this is easier to apply. Well, and if the reasons for this long optimization time are the same as why it stopped working at some part because the system because the eigenvalues will get complex. yeah, I'll try that with a purely real eigenvalue system, and then I'll get back to you.
Other questions?
I could ask about this, the K matrix we talked about in the beginning.
The K?
Yeah. I mean,
the controller game?
Yeah, the controller game. So how did this...
how I chose the K?
Yeah, exactly.
Oh yeah, that will, you will like that. It's an optimization.
Yeah, now when you say that, I remember that from yesterday. You said that. Yeah.
Yeah, this is actually, but the topic for this talk wasn't really the controller games for this optimization. The focus was more on this on the state space transformation. So yeah, if you're interested in how the controller games are developed, the first this one, the first paper had part where this controller game is explained in greater detail. I think the thing with LMIs is that you have quite a lot of opportunity to form your controller gains or your optimization task to your specific needs, as well as keeping the structure as general as it can get. So, well, you already know that I really like the general approaches, where you can just fit in the model and it gives you the solution. So this is why I really like working with LMIs, because you can formulate your systems very general, and you just feed it to you feed your model into this, and you get the solution.
I have a high-level question. The systems with oscillation, which is related to the complex part of the eigenvalues. Intuitively, you have an issue, which is that as the oscillating thing shifts, you kind of lose track of where you are in the oscillation, and that tends to make the computation, or is one way to interpret what's going on with the loss of precision of these simulations. What is intuitively at a high level? I know that you have a plan for dealing with the complex parts of the eigenvalues. Can you say a little bit more about intuitively how that's going to work? I couldn't follow all the technical details there.
Yeah, I think it's because I didn't mention this because it doesn't really matter. Because you have, well, if you take into account your system with the complex eigenvalues, then you take into account the range of them.
Yep.
So as long as they don't overlap in some part, you're safe.
Yep.
So maybe I don't get the.
Okay. So for example, one interesting thing that came up with the talk about the exponential enclosures is that you basically can throw away the complex parts because you know that they're not going to be there at the very end. But it doesn't seem that this is something that happens here.
No,
so,
because we are throwing away those imaginary parts for systems which are real.
You know that they're real valued, so there's no place for the complex
the imaginary parts that you're referring to are something we put in there in order to facilitate our transformation.
Okay.
So we put them in virtually.
Yep.
And then we just cut them out.
Okay.
And that's the reason why we cut them.
Okay.
But if you have those eigenvalues here, they are the eigenvalues of the system, so you don't cut them out.
You don't keep. Okay. Yep. Okay. Good. This is a good distinction. Thank you.
I have a question. In the beginning, you defined this concept cooperative, that the systems were cooperative. Could you come back to that and try to explain that a bit more to me?
Mm-hmm.
What is meant by
okay. It's I get that this is can be a bit confusing because of the explanations. Because there is a kind of confusing part, which is Metzler, Hurwitz, and cooperativity. And then you get positivity of the system as well. So maybe I can, the Metzler structure of the system is all off-diagonal elements are strictly non-negative. This is the Metzler function, or the Metzler structure. This also means that the system is positive. So the positivity of the system means that we stay in the same orbit.
We stay in the same orbit.
In the same orbit of the trajectory. And now if we get, I think it was here, the Hurwitz stability of the system is given by the diagonal elements which are negative, which represent the eigenvalues. So negative eigenvalue stability. And altogether is cooperativity.
Mm-hmm.
Altogether the system makes the system cooperative. Was this
It is expressed in abstract form.
Okay. Well, let's just say
if there was a
Maybe you
real
could make a
system.
sketch of how the simulation would look like for a cooperative system.
well, the simulation of a well, thanks for that. Well, it's just the I don't need to draw this actually because this is exactly the simulation of the first slide. So for cooperative systems, okay, yeah, I get what you say. Okay, well, it is similar to the part of the system. You need to stay in the positive order. So that means that for cooperative systems, we simulate the lower bound as a known system. So, and we can also simulate the upper bound as a decoupled system. If the system wouldn't be cooperative, then we could have something. Could be that we have something like this.
Yeah.
So
You can almost see something like this in the diagram of the pendulum. So if you switch on the pendulum, maybe I can. This is a question.
yeah, there is.
So you can see the upper bound seems to switch to become the lower bound around 0.2. Yeah. And if a system can do that, then you are not able to just simulate the lower bound to get the lower bound. You have to work with the whole set. And that's the big advantage of cooperativity. It means that this can't happen.
Yeah, it's I think for someone who hasn't worked with uncertainty a lot or with interval arithmetic, it's a bit confusing because you would trivially assume that you can just calculate the lower and the upper bound and you're done. But this what happens here is exactly the problem in doing so. So we kind of abstractly use the behavior of cooperative systems, which are mathematically structured as Metzler and Hurwitz matrices, to use our trivially idea of solving interval arithmetic. I hope this didn't confuse you further.
Yeah, I like this illustration. I understood the definition, but I didn't understand this consequence. That's a little nice. Yeah.
I think this. These consequences are. Well, as I said, if you do not work with intervals, then you would assume it's always like that. But we discussed this yesterday when I told you that the minima and the maxima may change, and it's quite difficult to take this into account with non-cooperative systems.
It's really a good question that you asked, Tony, because this shows why this is so cool. Is that if you're able to establish or get the systems to be in a cooperative form, then you can do the analysis much more efficiently than you would normally.
Well, the problem here is that due to our transformation matrices, for this I kind of promised that we have closed bounds because of this exactly known system. The problem here is with our transformation matrices, we put in another uncertainty because we built the hull over all eigenvectors, and well, the much larger the initial interval is, the much larger our eigenvector hulls will get. And this means that here we get another overestimation, so we're kind of shifting the wrapping effect into our transformation matrices. So one has to be very aware of the fact that we cannot just use this as an exact solution. So yeah.
Can you transform this into some kind of design rule for a control systems engineer?
Interesting.
I didn't understand this.
Can you transform this knowledge into a kind of design rule for a control system engineer?
I'm trying
What does
to.
it mean for you when you switch your hat into a control system?
Yeah. Actually, the idea why I wanted to do this is to test my control design.
Yeah.
So I was assuming that the interval will reduce, and I couldn't show this because of the wrapping effect, because of interval arithmetics. So my primary goal was to show or to use this as a control engineer. So actually the mathematical restrictions I think have to be designed for each model. So currently I'm trying to shift the knowledge into different models, so that I can say, okay, for this model we always have to apply a transformation with complex eigenvalues. Or for this one, it's clearly this will clearly be able to be solved with purely real eigenvalues. So in the future, I do want to know, or I do want to keep or give design examples, but right now I don't have the knowledge to select them.
You just have to test afterwards.
For now, yes. But I'm really high expecting of this inverted pendulum, because at first I thought, well, this will be the easiest problem to solve, and now it's it's the most tricky one. So I think this will help in understanding a lot of other models and a lot of other behaviors because of all the drawbacks this simple system gives. So having high expectations for the outcoming knowledge.
Yeah, but I mean, you as an engineer would like to have rules for design for verifiability, design for cooperativity, design for stability, design for blah blah blah.
Yeah, and this is the main goal for the future, that we can distinguish this. Because right now it's kind of trial and error.
Yeah, and for some it is also a bit too abstract.
Yeah, I had to mention.
So really good question, and I think that maybe one can say, and maybe it would be interesting, very interesting to hear what you think about this. If you want to make a guideline for designing for analyzability, these are analysis tools, and the question here is, how do you build systems that you can analyze? And if you want to design for analyzability, one solution is to stick with linear systems, because those are, one of the easiest ones to analyze. And people have been doing this for a lot of different problems. The challenge is that for many systems you have nonlinearities, and you have to go outside this. And then what classes to go with, what restrictions are practical, is pretty tricky.
Yeah, but I think the more models you test, the more clearer it will become for which simulation or which standard is going to, or which design is going to be successful in what. So, I mean, after all, the inverted pendulum is stabilized by our bachelor students. So, to be quite honest, this wouldn't be a real-life application. Or if we would see it from the engineer's view, then it wouldn't make sense to stabilize the inverted pendulum with an LMI and a cooperative system and prediction where to go. This is just a simple method to get to know the system's behavior and what can happen and what not, and this is what I'm trying to learn here. So after all, I do want the general knowledge, and I do want this to apply to systems where it does make sense. So I think the main part for real life applications that we got with this research topic was that the thermodynamical behavior of a solid oxide fuel cell, which we are working on, is cooperative. And we didn't have to transform this, which was quite nice, and it facilitates everything. So we got something out of it already.
Could you show this simulation graph you had, that you started with, a nice figure there? This. Yeah, the previous, the red one.
The red one. Mm-hmm.
So on the y-axis you have some state information, or?
Yeah, this is okay. I didn't tell you, but this is also the inverted pendulum.
Yeah.
Yeah, of course, because this was the problem
position
child.
of the pendulum.
Yeah, it's the angle of the pendulum.
It's not a feedback control.
It is. There is. I implemented this control approach where I started to adapt the controller gains according to the interval with my LMI controller, and I hoped that when the feedback gain turns constant, then my interval will reduce. So, and as you can see, the interval controller gains done by the LMI controller do exactly as I was expecting. And this overestimation here is a result of implementing the Taylor series expansion of the peak iteration. And this is also already reduced for stability, for example, because we're using, mostly when our applications, we're using physical information as well. So we know, for example, that everything, or we research if some of those intervals can be shortened or can be made smaller because of physical restrictions. Because as I already said, this is a stabilized system. So if there are some unstable intervals, then you can avoid, and then you can reject them because they are not included in the system. So this is already a reduced interval. So the mathematical solution would be even wider.
So the time here, what does it show?
Yeah, right. The time. Just this is purely mathematical.
Yeah.
please do not name me on the time constants or something like this, because the problem here really was to show the overestimation because of the.
But this time,
it is 1 second.
Yeah, but what is the time step in your iterations and things like that?
And now in my iteration, the time step was 1 millisecond.
So it's so you could have written time steps instead here and 1,000 to the
Yeah.
right.
Yeah. It's 1,000 times different.
So a quick question about this. It relates to future work integrating with exponential enclosures and this. So when you said tailored expansion, so it's polynomial enclosure here.
Mm-hmm.
Okay. Is it conceivable that if you just switch to the exponential enclosures here, you would get better results?
Probably.
Probably. Okay, cool. So this is an example of where one expects that exponential enclosures can help.
We're actually working on a joint approach of the exponential enclosures and the cooperativity.
Yeah. Okay, so this would be an example to illustrate the benefit of that.
Yeah, I implemented this for a paper which is now under review, and I compared the interval width of this simulation to the interval with our new approach with the exponential enclosure techniques, and it obviously was way better.
Awesome, very cool.
It was way better, and you didn't have this overshoot because here the control goal was obviously the 0.
Yep.
And you didn't have this overshooting.
Very interesting. So you don't see this kind of flipping effect. Very interesting. Very cool. This is good news for anybody implementing exponential enclosures right now. Any other questions? I have maybe one final question. I heard about we heard things come up about design principles, and we heard about dissipation. Sometimes people use dissipation as a principle for designing stable systems. Is there any easy connection between dissipative or passive, dissipative, the system being dissipative, and cooperativity?
Not that I know of.
Okay. Because these things were mentioned a couple of times.
Dissipation sounds like a reformulation of damping. Or
Yeah.
Yes.
Yeah. It's like basically.
And I would say from just a feeling, just a gut feeling here.
Yeah.
I'm just chewing. So I would think that this would be contrary to cooperativity, because you get another in the Lagrangian algorithm,
Yep.
you get another non-conservative force, and from my understanding, this just for the location in the StateSpace representation, I think this will get to the off diagonal, and I don't think this in the control system, and I don't think this would be positive for our cooperativity.
So there could be a conflict.
Yeah, I'm pretty sure there will be.
Very cool.
Yeah, this relates a bit to this kind of multi-agent systems research on very often have this kind of matrix structure of your matrix and agents moving around. But there I know some people are using these kind of passive approaches to control. But I don't think that these systems are passive or anything like that. But but I think people are using the techniques from that field. So, but no, but I actually thought about passive systems yesterday in some context when you were talking in the end there. But I guess there's no real relation here.
I think it's
But since you mentioned yesterday's talk, what you could do is, if you have a passive system, you can very easily get a Jacobian function candidate.
Exactly, this was
If you have a bot-controlled Hamiltonian system of dissipation, you right away have to have Hamiltonian serving as the corresponding Jacobian function candidate. And with this, you can, for example, rule out unphysical behavior in a consistency test. What I mentioned, for example, like conservation of energy. And everything that is contradicting that, also the positivity constraint.
Yes.
This can be cut off from a simulation.
Yes.
But I fully agree with what Julia said concerning cooperativity. I think also doesn't help at all.
I think it depends on which order you're considering. Because right now I consider the order first stabilizing, so first controlling, and then cooperativity. Because it will get very difficult if you put in your we did this actually with our thermodynamical system of the SOC. Well, the system was cooperative, but now you put in some controller gains, and where do you put them? Well, in the system matrix. And what does it do to your system matrix? Well, it rearranges all your entries. So it's kind of if you have the cooperative system, you should preserve this. And every let's say input you're doing with the system, you should do before.
Should the non-cooperative system generate more dissipation than the cooperative system?
I think we're starting on a new research problem.
I actually have no idea.
And this is a hallmark of an expert, to know where your knowledge stops and your the unknown begins. All right. So, well, on this note, I would like to thank you one more time, Julia, and to present you with a small token of our appreciation for the presentation. Thank you very much, Julia, for coming.
Thank you too.
Thank you for the presentation.